In 2007, a man named Jeremy Harper locked himself in his apartment in Birmingham, Alabama, turned on a webcam, and started counting. 1, 2, 3. He counted for 16 hours a day. He barely slept. He barely ate. His girlfriend left him somewhere around 700,000. He started hallucinating from the isolation. And 89 days later, he finally reached 1 million. 1 million numbers. 89 days of his life gone. Now here is where this gets interesting. Because Jeremy Harper holds the world record for the highest number a human being has ever counted to out loud. 1 million. That is the ceiling of human counting endurance. And the Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. So if you wanted to count every single star in our galaxy, one by one, how long would it actually take? The answer is so absurd that it breaks your brain a little bit, because depending on how you run the numbers, we are talking anywhere from 10,000 years to almost 100 million years. And the more you dig into why, the stranger this whole thing gets. Because it turns out that counting stars is not just mathematically impossible for a human lifetime. It is philosophically impossible. We cannot even agree on how many stars exist in the first place. We cannot see most of them. And the ones we can see, we have been trying to catalogue for over 2,000 years, and we have barely scratched the surface. But before we get to the timeline, we need to understand what we are actually dealing with. And that starts with a deceptively simple question that astronomers still argue about to this day. How many stars are actually in the Milky Way? You would think this would be a settled number by now. We have sent telescopes into space. We have mapped billions of celestial objects. We have technology that would look like magic to someone from even 50 years ago. But when you ask astronomers how many stars exist in our galaxy, they give you a range, and that range is enormous. The low-end estimate sits around 100 billion stars. The high end pushes toward 400 billion. That is a 400% margin of error. Imagine asking someone, how many people live in your city? And they say somewhere between 1 million and 4 million. That is the level of precision we are working with here. David Kornreich is an assistant professor of physics at Ithaca College, and he has spent years explaining this problem to students and journalists. His assessment is blunt. You cannot just sit around and count stars in a galaxy. It is a surprisingly difficult question to answer. Jeremy Darling at the University of Colorado puts it differently. Trying to count stars in the Milky Way is like trying to count trees in a forest while you are standing inside the forest. You can see the trees nearby, but the deeper you look, the more they blend together and block each other from view. The methods astronomers actually use to estimate stellar populations are indirect and build on layers of assumptions. First, they calculate the total mass of the galaxy by studying how fast it rotates. Stars and gas and dark matter all orbit the galactic center, and the speed of that orbit tells you how much gravitational pull exists at different distances. The Milky Way weighs in at roughly 1 to 1.5 trillion solar masses. That sounds like a lot of stars, until you realize that most of that mass is not stars at all. Dark matter makes up the vast majority of our galaxy's mass, somewhere between 90 and 97%. The stuff we can actually see and interact with, the stars and gas and planets and dust. accounts for maybe 3 to 6% of the total. So you take that relatively small slice of baryonic matter and you try to figure out how much of it is locked up in stars versus floating around as interstellar gas. But here is where the assumptions really start to pile up. To convert stellar mass into a number of individual stars, you need to know the average mass of a star in the Milky Way. And that depends entirely on how many small, dim stars exist compared to large, bright ones. This is called the initial mass function, and it describes how star formation tends to produce way more small stars than large ones. The problem is that small stars are incredibly hard to see. A red dwarf, which is the most common type of star in the galaxy, might emit only 1/100% of the light our sun produces. From any real distance, these stars are essentially invisible. So when astronomers estimate between 100 billion and 400 billion stars, what they are really doing is making educated guesses about how many invisible objects exist based on the visible ones they can detect. And those guesses keep changing. A study published in 2025 by Jianhui Lian at Yunnan University suggested that the Milky Way might have only half the stellar mass that previous estimates assumed. If true, that would shift all of our star counts downward significantly. The uncertainty is not a failure of science. It is a reflection of genuine cosmic difficulty. We are trying to inventory a structure 100,000 light years across while sitting inside it, blocked by dust, limited by physics, and unable to see the majority of what we are trying to count. But let us work with what we have. Let us take the middle estimate of around 200 billion stars and ask what it would actually mean for a human being to count that high. The math starts simple and then gets horrifying fast. If you could count 1 star per second without ever stopping, no sleep, no breaks, no breathing time between numbers, you would need approximately 6,300 years to reach 200 billion. That is longer than all of recorded human history. The first writing systems emerged around 5,000 years ago. You would need to count for longer than humans have been keeping records of anything. But nobody can count 1 star per second continuously. Jeremy Harper, the world record holder, averaged about 5 seconds per number when you factor in pronunciation time, breathing, and the increasing length of larger numbers. Saying 743,921,658 takes a lot longer than saying 7, and he was only counting for 16 hours a day because human beings need to sleep. At Harper's demonstrated pace, 16 hours a day at 5 seconds per number, counting to 200 billion would take approximately 48 million years. And that assumes no breaks, no illness, no aging, no death. You would need to live for 48 million years of continuous counting effort. For reference, modern humans have only existed for about 300,000 years. Our entire species would need to live and die 160 times over before the count finished. Even the optimistic calculations are depressing. Say you found someone who could maintain 1 count per second for 8 hours a day, 5 days a week, with weekends off and 2 weeks vacation. That is a reasonable human work schedule. At that pace, counting 200 billion stars would require approximately 19,000 years. You would need to start counting at the end of the last ice age, when humans were just beginning to develop agriculture. and you still would not be finished today. And remember, 200 billion is a middle estimate. If the true number is 400 billion, all of these timelines double. This is the first thing that makes star counting impossible. The human lifespan is simply too short by several orders of magnitude. But that is just the beginning of the problem. Because even if we ignore the time issue entirely, there is another barrier that makes counting fundamentally impossible. We cannot see most of the stars. When you walk outside on a perfectly clear night, far from any city lights, with no moon in the sky and excellent vision, you can see roughly 9,000 stars with your naked eyes. That sounds like a lot until you do the math. 9,000 divided by 200 billion equals 0.0000045%. You are seeing less than one star in every 20 million. And the reasons why are both frustrating and fascinating. The most obvious problem is distance. Stars follow the inverse square law of brightness, which means that a star twice as far away appears 4 times dimmer. 10 times farther means 100 times dimmer. The Milky Way stretches about 100,000 light years from edge to edge, and we are sitting roughly 26,000 light years from the center. Most stars in the galaxy are simply too far away for their light to register in human eyes, even though that light is absolutely reaching Earth. But distance is actually the smaller problem. The bigger issue is dust. Interstellar space is not empty. It is filled with tiny particles of carbon and silicate dust, and this dust absorbs and scatters visible light. Astronomers measure dust extinction in magnitudes, and in the plane of the Milky Way, you lose about 1 magnitude of brightness for every 3,000 light years of distance. That does not sound like much until you realize that the magnitude scale is logarithmic. Every 5 magnitudes represents a 100-fold decrease in brightness. By the time you try to look toward the galactic center, 26,000 light years away, through the thickest part of the galactic disk, dust has blocked so much light that we functionally cannot see anything in visible wavelengths. The extinction towards Sagittarius A, the supermassive black hole at the center of the Milky Way, reaches 25 to 30 magnitudes. At 30 magnitudes of extinction, fewer than 1 optical photon in 1 trillion makes it through. You would need 1 trillion times more sensitive eyes just to see what is there. Walter Baade, one of the great observational astronomers of the 20th century, spent years in the 1940s searching for an optical window toward the galactic center. He found a small region called Bade's window, where dust is slightly thinner, allowing glimpses of the inner galaxy. But even through that window, we see only a tiny fraction of the stars that actually exist in the galactic bulge. Then there is the problem of red dwarfs. These dim, cool stars make up 70 to 75% of all stars in the Milky Way. That is not a small minority. That is the overwhelming majority. And not a single red dwarf is visible to the naked eye from Earth. Think about that. Proxima Centauri is the closest star to our Sun. It sits just 4.24 light years away, basically next door in cosmic terms. And you cannot see it without a telescope. It is a red dwarf, and red dwarfs are simply too dim to see without optical aid, even when they are closer than any other star in the entire universe. So when you look up at the night sky, you are seeing a biased sample. You see the bright stars, the blue giants and supergiants that pump out enormous amounts of light, You see the closer stars that are near enough to Earth for their photons to register. But you are completely blind to the vast majority of the stellar population, the countless dim red dwarfs and distant objects that make up most of the galaxy. The dominance of red dwarfs deserves more attention because it fundamentally shapes what the galaxy actually is versus what we perceive it to be. Red dwarfs are stars with masses between about 8% and 50% of the Sun's mass. Below 8%, objects cannot sustain hydrogen fusion and become brown dwarfs instead. Above 50% or so, stars are hot and bright enough to appear orange or yellow or white. Red dwarfs burn their hydrogen fuel incredibly slowly. The smallest ones, barely above the fusion threshold, have surface temperatures around 2,000 degrees Celsius compared to the Sun's 5,500. They emit mostly infrared radiation rather than visible light, and because they burn so slowly, they live almost forever by astronomical standards. A red dwarf with 1/10 the Sun's mass can shine for roughly 10 trillion years. The universe is only about 14 billion years old. This means that every red dwarf that has ever formed in the history of the cosmos is still shining today. None have had time to die. They are all still there, steadily burning, too dim to see but vastly outnumbering the flashier stars we can detect. By contrast, the bright blue stars that dominate our night sky view are profligate spenders of their nuclear fuel. A blue giant might burn through its hydrogen in just a few million years before exploding as a supernova. These stars live fast and die young. They are spectacular but temporary. The red dwarfs are the permanent residents of the galaxy, the working class majority that keeps the lights on century after century, while the celebrity stars flame out in spectacular deaths. If you could somehow perceive infrared light with your eyes, the night sky would look completely different. The scattered bright stars you see now would still be there, but they would be joined by a vast background glow of red dwarfs. The Milky Way band would blaze with the combined light of billions of dim stars that currently remain invisible. You would see the galaxy as it actually is, not the biased sample evolution equipped you to perceive. This is exactly what infrared telescopes have revealed. The Spitzer Space Telescope, which operated from 2003 to 2020, observed the universe at wavelengths from 3 to 160 micrometers. At these wavelengths, interstellar dust becomes partially transparent. Stars that are completely invisible in optical light suddenly appear. Spitzer's Glimpse Survey, which stands for Galactic Legacy Infrared Midplane Survey Extraordinaire, mapped 360 degrees of the Milky Way's disk and revealed stellar populations utterly hidden from visible light observations. The James Webb Space Telescope, launched in December 2021, continues this tradition with even greater sensitivity. Webb observes at wavelengths from 0.6 to 28.5 micrometers, overlapping both visible light and deep infrared. Its images of star-forming regions like the pillars of creation show thousands of young stars embedded in dusty cocoons that the Hubble Space Telescope's visible light cameras could never penetrate. We are finally seeing what has been hidden all along. This creates a philosophical problem with the whole counting exercise. How can you count something you cannot see? The obvious answer is that we use telescopes. And this is where the story of star catalogues becomes genuinely inspiring. because humans have been trying to inventory the heavens for over 2,000 years, and the progress has been extraordinary. The first systematic star catalogue in the Western tradition was created by a Greek astronomer named Hipparchus around 129 BCE. Working on the island of Rhodes with nothing but his eyes and some clever instruments for measuring angles, Hipparchus recorded the positions and brightnesses of approximately 850 stars. He also invented the magnitude system for categorizing stellar brightness, a system that astronomers still use today with modifications. What prompted Hipparchus to create this catalogue is a story in itself. Ancient sources suggest that he witnessed a new star appearing in the sky. What we now know was probably a supernova. A star that should not have been there suddenly was. This spooked him enough that he decided to map the heavens in detail so that future generations could tell if stars were appearing or disappearing. He was creating a celestial inventory specifically to detect change. Hipparchus's original catalogue was lost to history, but much of it survived through Ptolemy's Almagest, written around 150 CE. Ptolemy expanded the catalogue to roughly 1,022 stars and added detailed mathematical models for planetary motion. This combined work became the standard astronomical reference for the next 1,400 years. When Arab astronomers translated the Almagest into Arabic during the Islamic Golden Age, they preserved and refined this knowledge while Europe languished in relative scientific darkness. The next major leap came from Tycho Brahe, a Danish nobleman who built an observatory on the island of Hoven in the late 1500s. Tycho was obsessive about precision. He designed enormous instruments, some with arcs over 5 meters long, to measure star positions more accurately than anyone before him. His catalogue of 1,004 stars, compiled without any telescopic assistance, achieved accuracy of about 2 arc minutes. This does not sound impressive until you realize that Tycho was measuring the sky using giant metal devices and his own eyeballs. His dedication was legendary. When a windstorm damaged one of his instruments, he threw himself into the repair work with such intensity that he caught pneumonia and nearly died. Then came the telescope, and everything changed. John Flamsteed became the first Astronomer Royal of England in 1675, tasked with creating an accurate star catalogue to help British sailors navigate by the stars. He spent over 40 years meticulously observing, and his catalogue of nearly 3,000 stars was published posthumously in 1725. Flamsteed's work tripled the size of previous catalogues and set a new standard for positional accuracy. The German astronomer Friedrich Argelander pushed even further with the Bonner Durchmusterung, published in 1859. This survey catalogued over 324,000 stars in the northern sky, a 100-fold increase from anything that came before. Argelander's team examined the sky section by section, recording every star visible through their telescope down to about 9th magnitude. It was tedious work that took years, but it gave astronomers their first truly comprehensive view of the stellar neighborhood. But here is the critical point. Even 324,000 stars was still less than 2 millionths of 1% of the galaxy. The more we looked, the more we realized how much we could not see. But there is a more fundamental problem that took centuries to resolve. For most of human history, astronomers did not even know the galaxy existed as a distinct object. The Milky Way was simply a fuzzy band of light arcing across the sky. The Greek name Galaxias Kyklos means milky circle. People saw it but had no conception of what they were seeing. Galileo changed that in 1610 when he pointed his primitive telescope at the Milky Way and discovered it resolved into countless individual stars. There were far more stars than anyone had imagined, but the question of scale remained. Were all these stars roughly the same distance away, forming some kind of shell around Earth? Or did they exist at vastly different distances? William Herschel attempted to answer this in the late 1700s by counting stars in different directions and inferring the shape of the stellar distribution. He concluded that the Sun sat near the center of a flattened disk of stars. This was half right. The disk shape was correct, but the Sun's position was completely wrong. Herschel was fooled by interstellar dust, which blocks light preferentially in certain directions. Where he saw fewer stars, there were actually more stars hidden behind obscuring clouds. He had no way of knowing. Harlow Shapley revolutionized this picture in the 1910s by studying globular clusters, those ancient spherical collections of hundreds of thousands of stars that orbit the Milky Way. Shapley noticed that globular clusters concentrated heavily toward the constellation Sagittarius. His interpretation was radical. The globulars orbit the galactic center. If they appear concentrated toward Sagittarius, that is where the center must be. The Sun is not central at all. We inhabit the galactic suburbs, roughly 26,000 light-years from the core. This raised an even bigger question. Those fuzzy spiral shapes, visible through telescopes, objects like the Andromeda Nebula, what were they? Were they clouds of gas within the Milky Way, or were they separate galaxies entirely, island universes at unimaginable distances? The debate reached its crescendo on April 26, 1920, at the Smithsonian Museum of Natural History in Washington, D.C. Harlow Shapley argued for a giant Milky Way, perhaps 300,000 light-years across, with the spiral nebulae contained within it. Hipparchus argued for a smaller Milky Way and claimed the spirals were external galaxies millions of light-years away. This became known as the Great Debate, one of the most consequential scientific arguments in history. Neither man was entirely correct. Shapley had rightly displaced the Sun from galactic center, but overestimated the galaxy's size. Curtis correctly identified the spirals as external, but underestimated our own galaxy's extent. Astronomer Virginia Trimble later observed that Shapley and Curtis each had hold of portions of the correct elephant. Edwin Hubble resolved the debate definitively in 1924 by identifying Cepheid variable stars in the Andromeda Nebula. Cepheids pulsate at rates proportional to their intrinsic brightness, allowing distance calculation. Hubble's Cepheids placed Andromeda nearly 1 million light-years away. The spiral nebula were indeed separate galaxies. The observable universe had just expanded by a factor of millions. This history matters because it demonstrates how dramatically our understanding of cosmic scale has shifted. Ancient astronomers thought the stars might be just beyond the moon. Herschel revealed a galaxy of stars, but placed the Sun at center. Shapley displaced us to the suburbs. Hubble revealed billions of external galaxies. Each generation discovered that previous estimates were wrong by orders of magnitude. When we say today that the Milky Way contains 100 to 400 billion stars. We should remember this track record of persistent underestimation. Photography helped enormously with the actual star counting. The Henry Draper Catalogue, assembled between 1886 and 1949, recorded spectral classifications for over 225,000 stars. But the human story behind this catalogue is as remarkable as the data itself. Edward Charles Pickering directed the Harvard Observatory and needed workers to analyze the growing mountain of photographic plates arriving from the telescope. He turned to women who could be paid far less than men for the same work. This group became known as the Harvard Computers, and they transformed astronomy while being paid about 25 cents per hour, roughly half what a male assistant would earn. These women were not merely doing rote labor, they made fundamental discoveries. Williamina Fleming developed a system for classifying stellar spectra that became the foundation of modern stellar taxonomy. She also discovered the Horsehead Nebula in 1888 while examining photographs of the Orion region. Henrietta Swan Leavitt discovered the period luminosity relationship for Cepheid variable stars in 1912, the very relationship that would later allow Hubble to measure distances to other galaxies and prove the universe's true scale. Annie Jump Cannon refined the spectral classification system into the OBAFGKM sequence still taught today, and personally classified around 350,000 stars during her career. Cecilia Payne-Gaposchkin, though technically not one of the computers, used the same spectroscopic data to discover that stars are composed primarily of hydrogen, overturning the assumption that stars had the same composition as Earth. O. B. A fine girl. Kiss Me is the mnemonic astronomy students memorize for the spectral sequence. Each letter represents a stellar temperature class, from the hottest blue O stars to the coolest red M stars. The sequence was created by Cannon and has survived virtually unchanged for over a century, a monument to the precision of work done with glass plates and human eyes long before computers existed. The space age launched catalogues into an entirely different regime. The European Space Agency's Hipparchus mission, named in honor of the ancient Greek astronomer, operated from 1989 to 1993 and measured precise positions for over 118,000 stars. This was the first space-based astrometric survey, and it freed astronomers from atmospheric distortion that had limited ground-based precision for centuries. But Hipparchus was just the preview. The main event was Gaia. The Gaia spacecraft launched in December 2013 and spent over a decade mapping the Milky Way with unprecedented precision. The numbers from Gaia's third data release in June 2022 are staggering. 1.81 billion sources catalogued, positions measured to accuracies of 20 micro-arcseconds for the brightest stars. Each source observed between 70 and 140 times over the mission lifetime to track their motion across the sky. To understand what 20 micro-arcseconds means, imagine you could see a human hair from 10 kilometers away. You cannot, of course, but Gaia could measure the width of that hair from a distance of 10 kilometers. That is the precision achieved from a spacecraft orbiting the Sun at a point called L2, 1.5 million kilometers from Earth, where the combined gravity of Earth and Sun creates a stable parking spot. 1.81 billion stars is an almost incomprehensible accomplishment. Anthony Brown, who chairs the Gaia Data Processing Consortium at Leiden University, called it the discovery machine of the decade. And he is right. Gaia has revealed streams of stars torn from disrupted dwarf galaxies. It has mapped the spiral arms of the Milky Way in detail never before possible. It has measured the distances to stars so precisely that astronomers can construct three-dimensional maps of our galactic neighborhood. The discoveries from Gaia have rewritten our understanding of the Milky Way's history. The data revealed that our galaxy experienced a major collision with another galaxy about 10 billion years ago. This ancient smash-up left debris scattered throughout the galactic halo. Streams of stars with distinct chemical signatures and orbital patterns that betray their foreign origin. Astronomers named this ghost galaxy Gaia Enceladus, and its remains make up a substantial fraction of the stars in the inner halo. Gaia also discovered tens of thousands of new asteroids in our solar system, measured the wobble of stars being tugged by unseen planets, and detected stellar explosions across the galaxy. The mission operated as an all-seeing eye, recording everything that moved or changed or flickered over its decade of observation. More than 1,000 scientific papers have been published using Gaia data, with hundreds more appearing every year. But here is the sobering reality. 1.81 billion. Sounds like an enormous number, and it is, but the Milky Way contains somewhere between 100 billion and 400 billion stars. Gaia, the most advanced star mapping mission ever launched, has catalogued roughly 1% of the galaxy. When Gaia completed its observations in January 2025, mission controllers at the European Space Operations Center in Germany commanded it to fire its thrusters and enter a parking orbit around the Sun, where it will drift silently for centuries. The spacecraft had done everything it was designed to do and more. But the job of cataloguing the galaxy is nowhere close to finished. The Vera C. Rubin Observatory in Chile achieved first light in late 2024 and will begin its legacy survey of space and time in 2026. This telescope carries the largest astronomical camera ever built, a 3.2 gigapixel monster that will photograph the entire visible southern sky every few nights. When fully operational, it will generate 20 terabytes of data per night and eventually catalogue billions more stars. But billions is still only a single-digit percentage of the total. We have been counting stars for over 2,000 years. We have progressed from Hipparchus's 850 to Gaia's 1.8 billion, a 2 million-fold increase in our celestial inventory. And we are still at 1%. This is what makes the thought experiment of counting every star so fascinating. It is not just that the number is large, it is that we do not even have access to the objects we would be counting. We are trying to take inventory of a warehouse where 99% of the contents are locked in rooms we cannot enter and may never enter. But let us push deeper into the absurdity anyway, because when you start comparing galactic star counts to other enormous numbers, the scale becomes genuinely unhinged. One of the most famous comparisons was popularized by Carl Sagan. He suggested that there are more stars in the universe than grains of sand on all of Earth's beaches. This claim has been analyzed multiple times, and the analysis is surprisingly close. Phil Plait, an astronomer who writes for Scientific American, broke down the sand calculation in detail. If you assume Earth has approximately 750,000 kilometers of sandy coastline, with beaches averaging 50 meters wide and 10 meters deep, and if each cubic centimeter contains about 8,000 grains of sand, you end up with roughly 4 times 10 to the 20th power grains of beach sand. That is 400 quintillion grains. The observable universe, according to current estimates, contains somewhere between 10 to the 21st and 10 to the 24th stars. The exact number depends on how many galaxies exist and how many stars each galaxy contains, both of which have significant uncertainties. But the ballpark is 1 to 10 sextillion stars, so Sagan's claim was essentially correct, at least when comparing stars in the universe to sand on beaches specifically. If you include all sand on Earth, including deserts and ocean floors, sand probably wins. But the numbers are genuinely comparable, which is itself astonishing. The universe contains about as many stars as Earth contains grains of sand. Neil deGrasse Tyson offers other comparisons that hit differently. There are more stars in the observable universe than seconds that have passed since Earth formed 4.5 billion years ago. Earth has existed for approximately 1.4 times 10 to the 17th seconds. Stars outnumber those seconds by at least 10,000 to 1. There are more stars than words ever spoken by all humans who have ever lived. Linguists estimate that humans speak roughly 16,000 words per day on average. Multiply that by the roughly 117 billion humans who have ever existed, multiplied by an average lifespan of communication, and you get perhaps 10 to the 18th total words spoken in human history. Stars still win by at least 1,000-fold. Think about that for a moment. Every conversation ever had, every love letter ever whispered, every speech, every argument, every bedtime story ever told to a child, every word in every language across all of human existence. The stars outnumber all of those words combined by a factor of 1,000 or more. Your entire species has not spoken as many words as there are stars in the observable universe. Not even close. The physicist David Blattner offered what might be the most visceral comparison. If you took 10 drops of water and counted the molecules in those drops, you would arrive at a number roughly equal to all the stars in the observable universe. Water has about 3.3 times 10 to the 22 molecules per liter. 10 drops is about half a milliliter, giving you roughly 10 to the 21st molecules. That matches the stellar population almost exactly. These comparisons are not meant to minimize the universe. They are meant to show that very large numbers exist in multiple contexts. The atoms in your body, the connections between neurons in your brain, the grains of sand on a beach, all of these quantities approach cosmic scales because nature does not restrict enormous numbers to astronomy alone. But here is where the comparisons become unsettling. Your body contains approximately 37 trillion cells. That is about 100 times more cells than there are stars in the Milky Way. Your brain contains roughly 100 trillion synaptic connections, more than 200 times the galactic stellar population. The complexity inside your skull exceeds the complexity of your galaxy measured by simple object count. This does not diminish the universe, it elevates biology. The fact that evolution produced structures more numerous than stars, and that those structures think and feel and wonder about the cosmos, is itself a kind of cosmic accomplishment. But let us return to the counting problem, because there is one more dimension we have not explored yet. The question was how long it would take to count every star in the galaxy. But the galaxy is not static. Stars are being born and dying all the time. The inventory is changing while we try to take it. The Milky Way produces roughly 1 to 3 new stars per year on average. That does not sound like much, but remember that stars live for millions or billions of years. The current stellar population represents the accumulated output of over 13 billion years of star formation, minus whatever has died. Red dwarfs can burn for trillions of years, far longer than the current age of the universe. Some of the first red dwarfs that ever formed are still shining today and will continue to shine for aeons after our sun has become a cold, dark remnant. Meanwhile, massive stars live fast and die young. A blue supergiant might survive for only a few million years before exploding as a supernova. The very stars that are easiest to see, the bright giants that dominate our night sky view, are also the most temporary. Betelgeuse, the famous red shoulder of Orion, will explode within the next 100,000 years or so. Geological time is nothing to a star, but astronomical time passes quickly for the brightest objects. So imagine you could somehow count every star in the galaxy. By the time you finished, the inventory would already be wrong. New stars would have formed in stellar nurseries, like the Orion Nebula. Old stars would have exploded or faded. The number you counted would be obsolete before you could announce it. This is not a minor correction. Over the tens of millions of years required to count at human pace, the Milky Way would produce somewhere between 10 million and 100 million new stars. You would finish your count and immediately need to start over. The universe is not waiting for us to understand it. It is evolving, changing, creating, and destroying, whether we are watching or not. And this raises a question that sits beneath all the mathematics. Why does any of this matter? Why should anyone care how long it would take to count something uncountable? Part of the answer is humility. The sheer impossibility of the task puts human existence in context. We live for maybe 80 or 90 years if we are lucky. The count would take tens of thousands of times longer than a human lifespan. Our individual lives are not just brief compared to the universe. They are brief compared to how long it would take to merely enumerate the objects in our own backyard galaxy. Carl Sagan wrote about this extensively. He believed that astronomy was inherently humbling and character building because it forces confrontation with scales that dwarf human experience. When you understand that every star in the night sky is a sun, many of them with planets of their own, and that you can only see 9,000 of the hundreds of billions that exist, something shifts in how you think about importance. Your problems do not become trivial, but they become contextualized. You are a temporary arrangement of atoms on a small planet orbiting an average star in the outer suburbs of one galaxy among trillions. But Sagan also saw something else in the cosmic perspective. He saw connection. The atoms that make up your body were forged inside stars that exploded billions of years ago. The iron in your blood came from supernovae. The calcium in your bones came from stellar nucleosynthesis. You are not separate from the universe. You are the universe examining itself. Literally, the matter contemplating the matter. Neil deGrasse Tyson pushes back on the idea that cosmic scale should make anyone feel small or depressed. When he looks at the universe, he sees bigness, not smallness. He sees connection, not isolation. The fact that we are here at all, that the universe produced conscious beings capable of wondering how many stars exist, is itself remarkable. We are not diminished by the cosmos. We are expressions of it. The astronauts who have seen Earth from space often describe a profound shift in perspective called the overview effect. The term was coined by Frank White in 1987 after interviewing numerous space travelers. They described looking down at Earth and seeing it as a fragile blue marble with no visible borders, obviously finite, clearly precious. Many of them cry. T.J. Creamer, a NASA astronaut, reported that every single crew member he brought to the cupola window on the International Space Station ended up in tears. This is what cosmic scale does when you actually experience it. It does not depress, it recalibrates. The universe is vast beyond comprehension, and within that vastness, life emerged, consciousness emerged, and curiosity emerged. Something in the laws of physics allowed atoms to arrange themselves into beings that ask questions about how many atoms exist. That is not depressing. That is miraculous. But there is one more layer to this thought experiment that deserves attention, because while a human could never count every star, technology is getting closer to doing something like it. Gaia mapped 1.8 billion stars over 10 years. Future missions will map billions more. The Vera Rubin Observatory will generate catalogues of unprecedented size. Machine learning algorithms can now process astronomical data faster than human astronomers ever could, identifying and classifying celestial objects by the millions. So here is an interesting question. At what point can we say we have counted the stars? The answer depends on what counting means. If counting means having a human being point at each star and say a number, then the answer is never. That is physically and temporally impossible. But if counting means detecting and cataloguing, measuring and recording, then we are making progress. We have gone from 850 stars in Hipparchus's catalogue to 1.8 billion in Gaia's. Another factor of 100 would bring us to the low end of total galactic estimates. We might never count every single star, but we might achieve something like a statistically complete sample. We might understand the population so well that the specific identity of individual uncatalogued stars becomes irrelevant. We would know how many red dwarfs exist even without naming each one. The same way you can know a forest contains 10 million trees without tagging every trunk. This is actually how modern astronomy operates. Nobody expects to catalogue every star individually. The goal is understanding distributions and populations, structures and patterns. We want to know the shape of the forest, not the location of every leaf. But something is lost in that abstraction. There is a romance to the idea of counting, of actually enumerating each object one by one. When Hipparchus sat on Rhodes and recorded star positions, he was doing something personal. He looked at each star. He noted where it was. He gave it a number in his catalogue. That star was no longer anonymous. It was known. Gaia's catalogue is vastly more comprehensive, but it was not created through that kind of intimate observation. Photons struck sensors. Algorithms processed data. Numbers filled databases. No human being looked at most of those 1.8 billion stars and thought about them individually. They were counted in aggregate, which is scientifically valid, but emotionally different. The impossibility of counting every star is not just a statement about time and mathematics. It is a statement about attention. Human attention is finite. We cannot look at 400 billion individual things and appreciate each one. The universe exceeds our bandwidth. It contains more than we can hold in our minds, more than we can process, more than we can love. And maybe that is the final lesson of this thought experiment. The universe is not built to human scale. It was not designed to fit inside a human lifetime or a human mind. It exists at dimensions that exceed us. And yet here we are, trying to measure it anyway. We invented mathematics to describe what we could not count. We built telescopes to see what our eyes could not detect. We launched spacecraft to escape the atmosphere that blocked our view. Every generation of astronomers has pushed the boundaries further, mapping more stars, seeing more deeply, understanding more thoroughly. The job is not finished. It will probably never be finished. But the attempt itself is meaningful. So how long would it take to count every star in the galaxy? If you count one per second for 8 hours a day, somewhere between 10,000 and 40,000 years. If you count at a realistic, sustained human pace, somewhere between 24 million and 100 million years. If you want to actually see each star before counting it, you would need technology that does not exist to observe objects that are hidden behind dust and distance and the fundamental limits of physics. The honest answer is that we will never count every star. Not because the task is too hard, though it is. Not because we lack the time, though we do. But because the universe is larger than any inventory we could ever complete. It is larger than our lifespans, larger than our civilization, larger than our species might ever become. And it keeps creating new stars while we try to count the old ones. But here is the thing. We count anyway. We have been counting for over 2,000 years, from Hipparchus squinting at the night sky to Gaia beaming data back from 1,000,000 miles away. We went from 850 to 1.8 billion catalogue stars in 22 centuries. That is not nothing. That is actually extraordinary. The universe does not care whether we count it. The stars will burn whether or not we know their names. But we care. We care enough to spend centuries cataloguing points of light, building ever more sophisticated instruments, dedicating careers and lifetimes to mapping our cosmic home. We cannot count every star in the galaxy, but we can count as many as we can. We can look up at the night sky and know that for every star we see, there are 20 million we cannot. We can understand that we are embedded in a structure so vast that even thinking about its size requires imagination beyond ordinary experience, and we can do what humans have always done when confronted with infinity. We can try anyway. The stars are not going anywhere, and neither is human curiosity. The count continues. But wait, there is something we have not fully reckoned with yet, because everything we have discussed so far deals only with the Milky Way, our galaxy, one galaxy among trillions. The observable universe contains approximately 2 trillion galaxies, according to a 2016 study led by Christopher Consolis using Hubble Space Telescope data. And that number might be conservative. More recent analyses suggest 6 to 20 trillion galaxies, once you account for the small, faint ones that current telescopes cannot detect. Each of those galaxies contains somewhere between 100 million and 1 trillion stars, depending on size. Dwarf galaxies might hold only a few billion stars. Giant ellipticals like Messier 87 might contain 100 trillion. The Milky Way sits somewhere in the middle of the distribution, neither especially large nor especially small. If you multiply the number of galaxies by the average number of stars per galaxy, you arrive at estimates ranging from 1 sextillion to 10 sextillion total stars in the observable universe. Written out, that is a 1 followed by 21 to 24 zeros. 1 to 10,000 billion stars. At this scale, the counting thought experiment becomes almost satirical. If counting the Milky Way stars would take 100 million years, counting every star in the observable universe would take roughly 100 trillion to 1 quadrillion years. The universe is only about 14 billion years old. The sun will die in about 5 billion years. The last stars will burn out in about 100 trillion years. You would need the entire remaining lifetime of the stellar universe just to count what currently exists. And of course, the observable universe is not the entire universe. The observable universe is merely the region from which light has had time to reach us since the Big Bang. Beyond the cosmic horizon, space continues. How far it continues, nobody knows. Some cosmological models suggest the total universe is infinitely large. Others suggest it might be finite but unbounded, curving back on itself like the surface of a sphere. We cannot see beyond the horizon, so we cannot know. If the universe is infinite, then there are infinitely many stars, and you cannot count to infinity, not in any meaningful sense. Mathematicians have various ways of dealing with infinite sets, comparing their sizes and categorizing their structures. But a human count that goes 1, 2, 3 requires finite numbers at each step. You cannot verbally reach infinity. So the deepest answer to how long it would take to count every star is that it depends on what you mean by every star. Every star in the Milky Way requires millions of years. Every star in the observable universe requires quadrillions of years. Every star that exists might require infinity itself. But there is another angle here that deserves exploration. Because we have been talking about stars as fixed objects to be counted, but stars are not really fixed at all. They move. They orbit the galactic center, traveling at hundreds of kilometers per second. The sun takes about 230 million years to complete one orbit around the Milky Way. During that time, the stars around us shuffle and rearrange. The constellations our ancestors saw were not the same shapes our descendants will see. This means that even the concept of a static star count is somewhat misleading. If you spent 100 million years counting Milky Way stars, the galaxy would have rotated nearly halfway around during your count. The stars at the beginning would have moved to completely different positions by the end. In some sense, you would be counting a different galaxy than the one you started with. Stars also travel between galaxies. The Milky Way is currently in the process of consuming several smaller satellite galaxies, including the Sagittarius Dwarf Elliptical Galaxy and the Canis Major Dwarf Galaxy. As these smaller systems fall into ours, their stars become Milky Way stars. The boundary of the galaxy is not crisp. It is fuzzy, with streams of stars bridging the gap between gravitationally interacting systems. In about 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy. The two spirals will merge over the course of 1 billion years or so, their stellar populations combining into a single giant elliptical galaxy that astronomers have nicknamed Milky Way. At that point, the question of how many stars are in the Milky Way becomes meaningless. The Milky Way will not exist as a distinct object anymore. So when exactly should you count? The galaxy you are inventorying is a temporary structure, stable on human timescales, but fleeting on cosmic ones. Any count is a snapshot of a moment in an ongoing process of assembly and evolution. This brings us back to something fundamental about the nature of knowledge. We want numbers. We want certainty. We want to know exactly how many stars exist. But the universe offers us ranges and estimates, uncertainties and approximations. It offers us 100 billion to 400 billion, not a precise figure. It offers us catalogues that cover 1%, not complete inventories. It offers us temporary configurations rather than eternal truths. The scientific method has given us remarkable power to understand the cosmos. We can predict eclipses to the second. We can calculate the mass of distant black holes. We can model the first moments after the Big Bang. But even our most powerful tools produce estimates rather than exact counts when dealing with galactic populations. The uncertainty is not a flaw in the method. It is a feature of the problem. Some questions simply do not have precise answers, only progressively better approximations. And maybe that is appropriate. Maybe the universe teaches us through its resistance to easy answers. Knowing that we cannot count the stars is itself a form of knowledge. It tells us about the scale of things, about the limits of human capacity, about the nature of the cosmos we inhabit. The inability to count is not a failure. It is a discovery. Let me tell you about a few specific attempts to push the boundaries of star counting, because the human ambition here has been genuinely impressive. The 2-micron all-sky survey, usually called 2MASS, operated between 1997 and 2001. It used 2 highly automated telescopes, one in Arizona and one in Chile, to image the entire sky in near-infrared wavelengths. Infrared light penetrates dust much better than visible light, allowing 2MASS to see stars that optical surveys completely miss. 2MASS detected approximately 470 million point sources across the sky. That is about 250 times more objects than any previous all-sky survey. Using 2MASS data, astronomers discovered the Canis Major Dwarf Galaxy, which had been invisible to optical searches because it lies almost directly behind the galactic disk. They also mapped streams of stars being torn from disrupted satellite galaxies, revealing the Milky Way's violent, ongoing consumption of its neighbors. The Sloan Digital Sky Survey has been operating since 2000 and continues running today. It has mapped roughly 35% of the sky in optical wavelengths, cataloging several hundred million stars and galaxies. One of its most famous contributions was the discovery of the Palomar 5 tidal stream, a ribbon of stars being stretched out of a globular cluster by the Milky Way's gravitational tides. The stream extends across nearly half the sky, too faint and spread out for earlier surveys to detect. More recently, the Dark Energy Survey mapped 5,000 square degrees of the southern sky between 2013 and 2019, primarily looking for distant galaxies, but also cataloging hundreds of millions of stars as a byproduct. Each new survey adds to our inventory, building databases that astronomers will mine for discoveries for decades. But none of these surveys come close to comprehensive galactic coverage. They are deep but narrow, or wide but shallow. They focus on specific wavelengths or specific regions. The true number of stars remains beyond direct enumeration. Perhaps the most philosophically interesting counting effort is the citizen science project Galaxy Zoo, launched in 2007. This project recruited ordinary people to classify galaxy shapes in images from the Sloan Digital Sky Survey. The founders expected the task to take years. Instead, within 24 hours of launch, the project was receiving 70,000 classifications per hour. People wanted to help count the universe. Galaxy Zoo has since classified tens of millions of galaxies, with over 1 million volunteers participating. The project demonstrated something profound about human appetite for cosmic connection. Given the chance to contribute to real astronomical research, people lined up by the hundreds of thousands. They classified galaxies during lunch breaks and insomniac nights, applying human pattern recognition to images that would take algorithms years to process. Teachers used it in classrooms. Retirees made it their hobby. People from every continent and nearly every country participated in counting the universe. There is something moving about this. The universe is too large for any individual to comprehend, but collectively, distributed across millions of minds, we inch closer to understanding. Each classification is one tiny piece of a puzzle that no single person could ever assemble. The count continues, not because one counter is sufficient, but because many counters add up to something larger than themselves. This is how humanity has always tackled problems too big for individuals. We organize, we collaborate, we pass knowledge from generation to generation. The stars will outlast any one of us, but the project of understanding them will outlast us all. And that is perhaps the final lesson. The question of how long it would take to count every star assumes a single counter, working alone, progressing through an infinite list. But humans do not have to work alone. We build instruments, we write software, we organize projects, we share data. The Gaia catalog was not created by one person counting. It was created by thousands of engineers, scientists, programmers, and support staff working together for decades. The next major catalog will be built the same way, and the one after that. Each generation inherits the counts of previous generations and pushes further. Hipparchus gave us 850. We are now at 1.8 billion. Our descendants may reach tens of billions, hundreds of billions, trillions. The trajectory is clear, even if the endpoint is not. We cannot count every star in a human lifetime. But humanity is not limited to a single lifetime. The count passes from hand to hand across generations, each adding what they can before passing the task forward. The ancient astronomers who watch the same stars we watch would not recognize our instruments, but they would recognize our ambition. They would understand the drive to know, to measure, to enumerate, to push back against the vastness of the unknown. Hipparchus sat on Rhodes 2,000 years ago and counted 850 stars with his naked eyes. He could not have imagined Gaia, a spacecraft positioned at a gravitational balance point beyond the moon, measuring positions to millionths of an arcsecond. But he would have understood why we built it. He would have felt the same itch to know that drives every astronomer who has ever looked up. That continuity matters. We are part of a project older than any living person, older than most civilizations, and we will hand it forward to generations we will never meet. How long would it take to count every star in the galaxy? Longer than one life, longer than human history so far, longer perhaps than humanity will exist, but also not long at all, because the count never stops. Every telescope observation is a count. Every catalogue entry is a count. Every child who looks up and wonders how many stars there are continues the count that began when the first human noticed the night sky and started asking questions. The count takes forever, and the count takes place every day. Both are true simultaneously. We will never finish. But finishing was never really the point. The point is what happens while you count. The discoveries you make, the patterns you notice, the universe that reveals itself one star at a time. 9,000 stars visible to your naked eyes. 1.8 billion in the best current catalogue. 100 to 400 billion in the galaxy. 1 to 10 sextillion in the observable universe. Perhaps infinitely many beyond the horizon. The numbers keep getting larger, and so does our ability to grasp them. That is the story of counting stars. It is also the story of science itself. It is also, in some ways, the story of what it means to be human in a universe that does not care about our comprehension, but somehow produced creatures who demand it anyway. We cannot count the stars, but we cannot stop trying. And somewhere, tonight, another Hipparchus is looking up at the sky. Another Jeremy Harper is preparing to count something impossible. Another Gaia is being designed. Another telescope aimed. Another catalogue prepared. The count continues. It always has. It always will. Look up tonight. Pick a star. Count it. 1. Now multiply by everything you cannot see, everything you will never know, everything that exists whether or not anyone is watching. That is the galaxy. That is the universe. That is the scale of what we are attempting when we ask how long it would take to count the stars. The answer is forever. The answer is right now. The answer is that the question itself is more interesting than any number could ever be. And if that does not leave you staring at the ceiling at 2 a.m, wondering what it all means, then I have not done my job. Because the stars are out there, hundreds of billions of them, just in our galaxy alone. And every single one of them is a sun. Every single one could have planets. Every single one has a story that began in a cloud of gas and will end in a white dwarf or a neutron star or a black hole or an explosion that seeded the next generation. We cannot count them all, but we know they are there. And knowing that, knowing the enormity of what exists just above our heads every single night, transforms how we think about our place in the cosmos. We are small, unimaginably small, brief and fragile and local to one tiny rock orbiting one unremarkable star. But we are the part of the universe that asks how big the universe is. We are the matter that wants to measure itself, and that might be the rarest thing of all. How long would it take to count every star in the galaxy? Long enough to change you forever just by thinking about it. That is the answer, and it is the only answer that really matters. Because in the end, the counting is not about reaching a final number. It never was. The counting is about the act of looking up and wondering. It is about building telescopes and training computers and staying up late analyzing data. It is about the human refusal to accept that anything is unknowable, even when the numbers say we will never finish. We are small and brief and bounded by limits we did not choose. But within those limits, we reach. We always reach. And sometimes, if we are lucky, we touch something larger than ourselves. The stars will burn whether or not we count them. But something in us insists on counting anyway. And that insistence, that stubborn, beautiful refusal to look away from the infinite, might be the most human thing there is. Count the stars. You will not finish. Count them anyway. 1.